So welcome everybody to today's edition of the Gauge Theory Virtual. Today we're very happy to have Masaki Taniguchi, who's going to tell us about genus bounds from Floer K-theory.
Thank you for introduction, and thank you for giving me this opportunity to talk. I'd like to explain the genus bound from K-theory, and this is joint work with Hokuto Kon and Jin Miyazawa. And we have three parts in this talk. First, I explain the background of relative genus bound, and secondly, I explain the main result, which is called real 10/8 inequality for knots. And if time permits, I'll also explain the proof of real 10/8 inequality. So let's go to the first part. So first, let me introduce the fundamental object, which is called relative genus. So let me start with fixing an oriented closed smooth form manifold. And let's fix an element in the second homology of X. And in this talk, we regard this as the relative second homology of punctured form manifold with boundary. Okay. And now, for given oriented knot in S3, we can define the relative genus. So it is defined by, so it is denoted by G large X small x K, just a minimal number of the genus of S, where S is an, again, oriented properly embedded surface. In the punctured form manifold. Such that the boundary of S is equal to K, and the homology class of X, S is equal to X. Okay. So this is a definition of our main object today. So I'm considering the smooth embedding, but if you consider locally flat embedding, we can also define the topological version as well. And today, we are interested in the difference between the topological smooth genus and, smooth genus and topological genus. So this is the definition of main object. And if you consider the X as S4, this is nothing but the 4 genus of knot. And if you take a K as unknot, then it is nothing but the minimal genus in the embedded surfaces for closed form manifold. So this is very historical studied things. And today, I'd like to focus on the following things. So it is proven by Cochran and Teichner, and independently Schneiderman in 2010. So they claimed for any knot in S3 whose Aleph invariant is 0, then there exists some number n such that such that the relative genus of K in n copies of S2 times S2 with zero homology class is equal to 0. So yeah, this is proven by using so-called bandpass move. And so for not in S3, we say K is H thrice in closure form manifold X if the relative genus with zero homology class is equal to 0. So this is just a terminology. And we can, of course, define a topological version as well, just by replacing the smooth genus with topological genus. Okay.
Their result is for smooth?
Yes, smooth, for smooth genus. Yeah, 3. And so this theorem enables us to define the following knot concordance invariant for any knot with trivial RF invariant. We can define so-called stabilizing number, which is just a minimal number of such an n. So such that the K is H thrice in the n copies of S2 times S2. Again, we can do the topological category, the same thing in the topological category. So this is finite number by previous theorem. And the question what we focus on today is the following, raised by Conway and Nagel recently. So the question is there knot in S3 whose RF invariant is 0, such that there is essential difference between the topological stabilizing number and smooth stabilizing number. And precisely we need to assume this. So topological stabilizing number is strictly positive. Otherwise, it is easy to solve because if you take a topologically thrice knot but not smoothly, then it is an answer of this question. But if you impose this, it was difficult to obtain the non-trivial estimate for the smooth stabilizing number. So that was the situation. And by using topological concordance invariance, the three-symbol range signature in the same paper of Conway and Nagel, they provided a lower bound of topological stabilizing number. By using three-symbol range signature. So this is for topological stabilizing number. So what we want to do today is just giving the stronger estimate rather than this, so stronger than this estimate. And so this is the things. And let me just review several the genus bounds from the known, smooth genus bound of known series. So mainly there are two main studies for genus bounds, and one is for definite manifold. So for definite manifolds, there are a lot of tools to give a strong lower bound of smooth for genus. Let me just say the representative things. So in the figure fair theory, the Osbach-Savos tau invariant gives a lower bound in any negative definite form manifold. And in the common homology theory, Rasmussen invariant also give a lower bound in the S4. But recently, by the work of Manuelescu, Marengo, and Saka-Wills, they extended the genus bound result for the copiers, the connected sum of copiers negative, CP2 bar. And also in the instanton side, the Graham-Morokas invariant S-sharp also gives the lower bound for genus in negative definite form manifold. And recently, in the Seiberg-Witten side, it's a kind of equivariant Seiberg-Witten theory for branch of covers. Baraglia and Hekmati gave the family of invariants called theta p. And that also gives the lower bounding for negative definite manifolds. And actually, conjecturally, it is corresponding to the inner figure fair theory, Hendricks. Lipschitz circle. Hendricks Lipschitz circles equivariant figure fair invariant as a family. And these invariants are very strong enough, strong enough to show the Milnor conjecture. So, that was the situation for definite form manifold. But if you consider indefinite form manifold, so the situation will be rarely changed. So for the indefinite form manifold, there are again two studies, mainly two studies. And one is the using under the condition, under the non-triviality of form manifold invariant, like mixed invariant or Seiberg-Witten invariant or Bauer-Fuld invariant. And so let me review such kind of work. So in the Seiberg-Witten theory, there's a representative study for the adjunction inequality for indefinite manifold. So the Moroka law improved the adjunction type inequality for manifold with contact boundary. whose Krohn-Hamilton invariant is non-zero, mainly for symplectic fittings. So, and recently, by using Higraphia mixed invariant, Manescu-Marengo-Piccillo also provided the adjunction inequality for the manifold with non-trivial mixed invariant. And recently there are a lot of works about the Bauer-Furter invariant as well. So in the same paper of Marengo-Piccillo, they also gave the obstruction to being H thrice by using Bauer-Furter invariant and the usual Bauer-Furter invariant. And also recently, Ida Mukherjee and me gave the adjunction inequality by using the homotopical refinement of the Krohn-Hamilton type invariant. And also by using Bauer-Furter invariant with double Van cover construction, Baraglia gave the genus bounds for quasi-positive knots or quasi-positive rings. And again, the joint work with the Ida and Konno, we provided the generalization of the Ida Mukherjee Taniguchi's inequality here. Anyway, but for these inequality, these inequality are obtained by assuming the non-triviality of four manifold invariants. But now we want to focus on the four manifolds like the copy of connected sum of S2 times S2. So this method cannot be used here. So our idea is to use a 10/8 type inequality. So this is the main topic today. And let me just review again the studies. So in the same paper, in Marengo-Piccillo, they also provide the obstruction by using usual 10/8 inequality plus surgery technique. And the main topic today is this. So we provide the new knot concordance invariant, takes value in 1/16Z with real 10/8 inequality. Okay, so this is today's main topic. And later, so recently, Ian Montague also provided a similar inequality, a similar invariant called kappa vector, and with relative Boolean inequality. But these inequalities are actually independent, and it is also interesting to compare these inequalities. So that's the background of today. And by using our invariant, we can prove the following result. So there exists a sequence of knots such that the topological stabilizing number is strictly positive, and the difference between the smooth stabilizing number and topological stabilizing number goes to infinity if you if n goes to infinity. Okay, so that tells us the essential difference between the topological and the smooth stabilizing numbers. Okay. So let's go to the second part. But yeah, before that, do you have any question or comment so far?
Just in the statement of the theorem, do you know what the topological stabilizing number is?
Yeah, in this case, I'll explain later, but for example, Kn can be taken as the n copies of connected sum of 311 knot. And topological stabilizing number for this knot will be just 8n. But our inequality tells us the smooth stabilizing number of this guy is greater than or equal to 9n. But we don't know how to determine this guy. Yeah, so that's still open. So, okay, let's go to the second part. So main topic, real 10 over 8 inequality. So for given knot, we can provide so-called kappa invariant. It takes value in 1 over 16z. And we have the following property. So first of all, kappa is not concordance invariant. And the kappa of the unknot is equal to 0. And twice of kappa is equal to minus signature over 8 modulo 2. Okay. And also we have kappa k plus kappa meter of k is greater than or equal to 0. So these are the fundamental properties of these invariants. Yeah, so by using this invariant, let me write down the main theorem today. So 10 over 8 inequality. So let, again, X be oriented, closed, smooth form manifold. Satisfying the integral homology, first homology of X is equal to 0. Now let's take the second homology class of X. And suppose this is divisible by 2. In other words, this is 0 in the 0 over 2z coefficient. And the Poincare dual of second Sheffield-Whitney class of X is equal to x over 2 in 0 over 2z coefficient. So these are assumptions for the four manifold and homology class. And under this assumption, we can prove the following inequality. So minus signature over 8 of x plus 9 over 32x squared minus 9 over 16 signature of k is smaller than or equal to the plus of x plus the relative genus here of k plus kappa k. Yeah, so this is the main result today. Oh, yeah, okay. So it is slightly complicated. So let me just focus on the really simple case first. So if you put k as unknown and then kappa unknown is equal to 0. So just by putting the other case, then we have this inequality. So this gives a minimal genus bound for surfaces in closed form manifold. And let me say the remark. So this is actually essentially proven by Yuya Kato recently. So our inequality can be regarded as just a relative version of Kato's inequality. And let's again simplify by putting x as 0. Then this inequality is nothing but this inequality. And this inequality is almost nothing but Fruita's 10/8 inequality. So if you consider the zero homology class, then this condition actually implies x is spin. So yeah, we have spin condition here, and this inequality is almost nothing but Fruita's 10/8 inequality. So our result can be seen as some generalization of Fruita's 10/8 inequality as well. And our construction based on the double branch of cover constructions, and I think you can also imagine what our Manorescu's 10/8 inequality. So by just combining the Manorescu relative 10/8 inequality plus double branch of cover construction, we get some inequality, the similar inequality. But actually, yeah, this is really independent of our inequality. So it is related to the previous Ian's inequality, but our inequality is independent. Okay, so do you have some question or comment on the main theorem? No? So then let's focus on the several fundamental computations for kappa invariant. So if K is two-bridge node, then yeah, kappa invariant is just 1/16 signature of K. Sorry, I forgot a minus here. And this also holds for any linear combination, the connected sum linear combination of two bridge nodes as well. So this is one thing. As an example, if you consider so it's a torus node, our convention of signature is -2 for this guy. So that means this is equal to 1/8.
Does this proposition hold for, quasi-alternating knots or any knots whose some analog of that for knots whose branch double covers are L spaces?
So this is open. So this is kind of naive conjecture. So is it true for quasi-alternating?
And you don't even know it for alternating. You really only know it for two bridge.
Sorry?
You don't even know that your question for alternating. It's only for two bridge that you know.
Only for two bridge. But yeah, so this is the question. Yeah, open question. Is it true for quasi-ordinary? There's no counterexample at the moment. Yeah. And the second proposition is for torus knot. So let PQ be a coprime or the coprime integers. Oh, sorry, coprime. Then the kappa invariant of torus knot is -1/2 of the mu bar invariant of sigma 2, 2pq. Where this mu bar invariant is Neumann Zimmermann invariant. Defined by taking the graph bounded by the homology 3 sphere and find nice characteristic and consider minus signature over 8 plus the square of characteristic. That's rough definition of this invariant. Anyway, this is combinatorial invariant. It is not so difficult to compute. And this result also holds. So this is theorem. This result also holds for linear combination as well of torus knot. Okay. So these are the fundamental computations for the kappa invariant. So for example, the mu bar invariant of sigma 2, 3, 11 is 0. So that implies kappa invariant for T3, 11 is 0. And it is true for the connected sum of this knot as well. So yeah, this is what I use today. So this is the only input today. Okay, so now let's go back to the stabilizing number stuff. So in order to give some, in order to find some difference between the topological and the smooth category, we also need to determine the topological category, the stabilizing number. But yeah, so recently, by the several work, we can determine the topological stabilizing number. So this is again the Conway-Negron result. So under the condition of alpha invariant, we can give this upper bound for any not k. So topological stabilizing number is bounded by topological for genus. And also, there's some deep work in the topological side again. Bader and Banfield rework again recently gave the topological for genus bound for T3 K naught, so which is given by just a setting function of 2k over 3. So by just combining these two results, we can determine the topological for genus for example, connected sum of T3 11 knot. It is equal to 8m. Oh, note that the RF invariant of T3 node is 0, so we can define the topological stabilizing number. And so this upper bound for topological stabilizing number is just given by these two results. Okay. And lower bound is given by just a three-term signature. So for these nodes, actually the three-term signature is enough to determine the topological stabilizing number. So that was the situation. Oh, maybe I should use. Okay, now let's use our inequality to give a constraint for smooth stabilizing number. Okay, so this is the theorem. So the smooth stabilizing number of the n-connected sum of T311 node is greater than or equal to 9m. Yeah, it is not so difficult. So just we put the S2 times S2, connected sum of S2 times S2 here, and x as 0. And we know the signature of the T311 torus node, it's -16. And kappa invariant was 0 by non-algebra invariant. So just put all things, and then we obtain the following inequality. So we have this inequality. This is our inequality. And just this is -16m, and this is 0. So that easily implies this result. Okay. Okay, so let me say a few things for the kappa invariant. And there is some cross-link change formula of the kappa invariant by using this kind of inequality. And it is enough to determine the kappa invariant for the nodes with prime nodes with up to 9 crossings. Almost we can determine the kappa invariant after 9 crossings. And also it's open that if there is some topological slice node whose kappa invariant is non-zero, this is open. Yeah, so that is the situation now. Okay, so let's go to the proof.
Is there any good understanding of when or for what classes of knots the topological Floer genus and signature bounds are going to coincide? I mean, this is some kind of special family where the Tristan-Levine signature computes the topological Floer genus. Like, do we know of other families? I mean, outside of...
I think the...
I mean, like the 2n torus knots, of course, but...
2n torus knot?
Well, sure, but I mean, that's not that...
Oh, yeah, okay. I'm not sure. For example, 2 torus knot to 5 something, I don't have any idea about such kind of things. So because I think there's no complete formula like this.
Right. Yeah, I was just wondering. I mean, I think those folks, I had some impression that they were trying to kind of classify when that type of phenomenon occurred, and I didn't know what the status of that was, or if there's other kind of general families where the bounds agree. But okay, thanks.
Yeah, thank you. Yeah, that's still open. Yeah. So let's go to the proof. So there are 9 steps in the proof. Okay. So let me first go to the first part. And yeah, first let's fix the surface representing a minimal genus. Such that this is the homology class is equal to x, and the boundary of S is k, and S is properly embedded smoothly properly divided in x, and x is divided by 2, and x divided by 2 is equal to the Poincare divided over spheroid class. So that's a condition. Okay, so yeah. So now, in the first step, we take a double bond cover of this guy. So we can take a double bond cover because we assume the x is divided by 2, and we have covering involution iota. Okay. And by the second Stevie-Hoyt class condition, that condition, we know that this is spin, so that implies there is spin structure on this manifold. And by this condition, so we assume this strong condition. First homology of x is 0. So that implies there is a unique spin structure on this four manifold. And since spin structure is unique, the pullback of the by iota is isomorphic to the original spin structure. Okay. Let's take iota invariant Riemann metric on this four manifold with boundary, which is product near the boundary, precisely.
Is iota is the covering involution or the conjugation involution here?
Covering involution. Maybe I should write tau instead of iota. Sorry about that. Okay, so secondary, this is the first step. We take double bond cover and obtain the equivalent four manifold. And in the second step, just write down the Seiberg-Witten equation on the double bond cover. So this is a map. So let's fix the spin connection. So the spin connection is determined by Riemann metric. And let's write down the Seiberg-Witten equation. This is a map from I valid one form plus positive spinor bundle of spin structure to the self-dual part plus minus spinor plus the configuration for the boundary 3 manifold. But precisely, we need the slice on the global slice here. Let's ignore the technical things. And again, we actually need to take a sliced configuration. And so this is a configuration space for 3 manifold. So as a restriction of spin structure, we can have a spin structure here, and we can write down the spinor bundles and spin connections, and spin sheet connections, and consider the 3-dimensional setting in here. Okay, so Seiberg-Witten map here is just a summation of the usual Seiberg-Witten invariant for four manifold with boundary plus the restriction part. So this is the Seiberg-Witten situation. And okay, so this is the second step. Just write down the Seiberg-Witten setting for four manifold with boundary. Okay, so next, in the third step, we take a lift of iota. Okay, so iota induces a map on the framed bundle. So this is induced map from covering transformations. And the spin structure is a map from the spin 4 bundle to framed bundle. So we have this map. So this is the principal spin 4 bundle. And here we can take the lift iota Childer, but the point is actually it is order 2. But actually, if you take a lift for which commits with this diagram, then it will be order 4. So iota Childer square will be -1. So on the fixed point, this can be the involution near the fixed point can be seen as 1 minus 1. And if you consider the lift, and let's regard the SP4 as SP1 times SP1, then yeah, you can easily check that the lift of this guy corresponding to I minus I or minus II. Anyway, we cannot take the order 2 lift on spin structures. So let's take a lift iota Childer. And of course, iota Childer also induces a map on the spinor bundles. And again, the square is -1. So and here is a non-trivial thing. So we don't want to do the equivariant Seiberg-Witten theory for this order 4 action. So what we want to do is define the involution I, which is obtained by the composition of J and this action iota Childer. So J is an element of quaternion. So this will be order 2. And also, since I multiplied J, this is anti-linear. So this can be regarded as a real structure on the spinor bundle. So
can you say why is this? Why wouldn't you just look at iota tilde, the order 4 thing? Is it just too complicated?
So yeah, so we wanted to work on the fixed point part of the that theory. And if you think about the fixed point part of the order 4 action, this order 4 action, then spinor will be 0. So we cannot obtain an interesting theory for a fixed point part of the Floer homotopy type. But if you consider this action, yeah, the fixed point part is still non-trivial, and we can obtain interesting constraint. Yeah, that's why. Yeah.
Okay, thanks.
Yeah. So this also acts on domain and codomain of F, naturally. And since it commits with the Clifford multiplication and Dirac operator, and the action on the gauge group of the gauge group, so this naturally acts on the setting of Seiberg-Witten equation. So yeah, but yeah, this has many historical background, I think. So at least Wang and Tian use this kind of stuff to define the real invariant in the almost complex 4 manifold. Yeah, with Seiberg-Witten setting, and of course this is considered by Yuya Kato again. Okay, so
Do you expect there's some like relationship between this action and the corresponding one in Heegard-Floer theory? I mean, this is something similar to, like
yeah.
you can also do this in Heegard-Floer. It's been
I think so.
considered.
So our conjecture is like this is corresponding to tau in the Heegard theory with iota maybe. Yeah. Okay, so let me say the remarks. Sorry, before that, let's go to the third. So this is the third step. Just take a lift and consider this anti-linear involution. And we have real structure from that. And take a fixed point path theory. Okay. So take fixed point. So the fixed point path for Seiberg-Witten equation. So since the Seiberg-Witten equation is equivariant with respect to this action, so we can consider the fixed point part. And we need to calculate Fredholm indices. So let me just say, so if the Seiberg-Witten map F can be written as the real part corresponding to adjacent single plus complex part corresponding to the Dirac operator plus projection plus other part, the compact part. So if you write down this, we can say the co-kernel of, so let me remind you, we are assuming the first homology, the B1 is 0, and so that implies double Banach cover of B1 is also 0. So let's ignore the B1 part. And then the invariant part, we need to think about an invariant part. And we need to put suitable spectral condition, but okay, if you put suitable spectral condition, then the co-kernel, the dimension of the co-kernel of this operator. So if you ignore the I, then it's corresponding to B plus of X, the double Banach cover. But in this case, it is rarely different. So it is equal to B plus of the double Banach cover minus B plus of iota of double Banach cover. So here, iota means just the invariant, iota invariant part, the dimension of the iota invariant part. So here is actually a big difference between the usual theory and the real theory. Yeah, so for example, if you consider the usual equivariant theory, the B plus should be corresponding to the B plus of double Banach cover or B plus of base space. But in this theory, the B plus is really different. So B plus is corresponding to B plus of double Banach cover minus B plus of the invariant part of the double Banach cover. And yeah, actually, this is very essentially to obtain the application to the stabilized number. So if you write down the 10/8 type inequality, the replacing with this is really important in our application. Oh, and reason why we have this kind of thing is just we call the action on this of this I is nothing but minus iota star. So if you consider fixed point part of I, then this is really corresponding to the minus iota fixed point part. And this is nothing but this. Okay, so yeah, this is kind of the most essential part in this theory. And if you think about the complex part, this is also, yeah, this is kind of automatically because we are considering the anti-linear involution, and also the Dirac operator commits with the involution. So that easily implies this is half of the usual index. Sorry. And so, yeah, this is, yeah, for example, if you write down the usual, by usual convention, this is 1/16 signature of this guy plus 1/2 of the usual correction term. maybe minus 3. I forgot the minus. Anyway, so the point is the spectral flow of this theory is nothing but half of the spectral flow of this theory. So there's no technical issue for example, the independence of the metric or such kind of things. Okay, so this is the fourth step. So just we calculate Frame indices. And in the fifth steps, we do the finite dimensional approximation of this nonlinear map Fi. Okay. So just take a finite dimensional approximation of this guy. So then, yeah, we obtain a map between the finite dimensional spaces. So this is machinery developed by Manorescu and also Frutas and so on. And anyway, we obtain a map from the one-body computation of some vector space to some space called SWF. This I fixed point part, and yeah, this is so-called relative Baufurter invariant, and we have some diffraction. Sorry, I forgot to say. Now we want to do some kind of 10-over-8 inequality, the constraint like 10-over-8 inequality. So we need a symmetry for in that setting. So, but the J action doesn't commit with the order element in the pin 2. The only symmetry we can use is actually this, Z/4Z. We cannot use the force symmetry. But actually, the Z/4Z is enough to show the 10-over-8 type inequality. So, okay, so yeah, just apply. Then next, so this is 5 steps. So we take a finite dimensional approximation, and yeah, this is also non-trivial part, and the step 6, where I have 2 minutes. Just in the step 6, we apply the case theory, the equivariant case theory. But precisely, we use the Thom isomorphism for equivariant case theory, so we need some orientation for that theory. And in order to do that, roughly speaking, we take the tensor product with C, which can be regarded as by taking the double of this map. So that is not so serious situation. So we can apply the Z/4Z equivariant case theory, and then we obtain the following diagram. So we have a map from here to here, here, and this guy. So this is just a fixed point. This is a fixed point part of these spaces, and just apply. So we have inclusion from here to here and here to here, and let's apply contravariant functor, this guy. Okay, so we have this diagram. And the maps like this. Okay. And the original kappa invariant is defined by just constructing the ideal obtained by the image of this guy. So original copper. So as in the case of original copper, we can define the kappa invariant using divisibility. So what is this means? So this means if you think about the case theory, D4 equivalent case theory for the point, this is isomorphic to the following two variable ring. B plus, yeah. And just think about, so we can compute this map explicitly. So this is like the 2 of power of something with omega. And just define the kappa invariant by considering the minimal divisibility of this omega or 2 is equivalent. So then, yeah, we can write down some constraint as in the case of original Taniguchi inequality. So that gives you, and this can be computed by using the invariant part of the Atiyah-Shinga operator and Dirac operator. So as a conclusion, so the divisibility implies this inequality. So this is a B plus part, and this is a signature Dirac operator part. And this is step 6. Yeah, sorry, and this is almost the essential part. And the latter part is kind of obvious because just we write these quantities by only using in terms of base. So this is base B plus of base manifold, and yeah, so B plus of Lagrange cover here is, yeah, so this is easy consequence of my arbitrary stuff. And yeah, let me finish writing. So yeah, so this one and this guy. Just put these things into here. Yeah, that's all. Thank you for listening.